Mm. First of all, I have to start with an apology. At the previous lecture, I promised you to prove an application of the polar decomposition. But for some time constraints, I decided to postpone the applications until the last lecture. So sorry about that. And so now we eventually came to the culmination of our course, namely to the spectral theorem for bounded self-adjoint operators on a Hilbert space. So this will be our subject for the last three, I suppose, lectures. Actually, the spectral theorem is not a theorem in the usual sense of the word. It's rather a collection of results which are closely related to each other and which tell us something essential about the structure of our operator, of our normal operator on the Hilbert space. So some people say that different forms of the spectral theorem are equivalent, or at least essentially equivalent to each other. In my view, this is not exactly the case. In fact, to deduce one form of the spectral theorem from another one, we have to do some work. It's not immediate and is not always obvious. So in summary, there are several different forms of the spectral theorem. All of them are very useful. They are closely related to each other, but they are not formally equivalent. And so today we discuss the first form of the spectral theorem, namely the spectral theorem in terms of functional models. Spectral theorem 1, functional models. Let's start with some motivation. So first of all, let's suppose that we have a finite dimensional Hilbert space, H. H is a finite dimensional Hilbert space. And suppose that T is an operator. So for simplicity, we assume that it is self-adjoint, a self-adjoint operator on H. Then you probably know from your linear algebra course that such an operator is diagonalizable in the sense that there exists an orthonormal basis in H such that the matrix of T with respect to this basis is diagonal. So this statement can be written in the following form. So this is our operator T. Then there exists a unitary isomorphism between H and C to the power n. This is a unitary isomorphism. So n is the dimension of H, and the unitary isomorphism is equivalent to a choice of an orthonormal basis in H. So there is a unitary isomorphism between H and Cn such that after we identify H and Cn, T becomes the multiplication by a diagonal matrix. So this means that T is unitarily equivalent to a diagonal operator on Cn. Okay, so this is a well-known result from linear algebra. Now let's look at an infinite dimensional analog, which many of you probably know about. So again, we take a Hilbert space. Now it is infinite dimensional. And for simplicity, let's assume that it is separable. Separable and infinite dimensional. And suppose that T is a compact self-adjoint operator on H. There is a classical result about such operators, namely the Hilbert-Schmidt theorem, which states that each such operator is also diagonalizable in a certain sense. Namely, we can draw the following picture. So this is our operator. Then there exists a unitary isomorphism between H and little L2. Which establishes unitary equivalence between T and suitable diagonal operator on the little L2 space, M lambda. So M lambda is just the diagonal operator. It takes a sequence xn to the sequence lambda n x n. So this is the essential part of the Hilbert-Schmidt theorem. What we're going to do now is to extend this result to non-compact bounded operators. Of course, this result needs some modification because we know that in the general case, a bounded self-adjoint operator doesn't have to possess the point spectrum. So in general, it is not diagonalizable in the usual sense of the word. Nevertheless, we're going to prove the following result. So suppose that H is a Hilbert space, and suppose that T is a self-adjoint, or more generally, a normal operator on H. Then it turns out that there exists a measure space such that our operator T is unitarily equivalent to a multiplication operator on the big L2 space, L2 of omega mu. So here omega and mu is a measure space, not necessarily finite. So this is this is one of the forms of the spectral theorem, the so-called spectral theorem in terms of functional modules. So clearly it generalizes both the Hilbert-Schmidt theorem and the respective finite dimensional results. So if T is compact and omega is the natural numbers and mu is the counting measure, then we get the Hilbert-Schmidt theorem. And in the finite dimensional case, so omega is finite and mu is the counting measure, and we get the respective finite dimensional result about the diagonalization of self-adjoint operators. Okay, so this is our plan. Now to begin with, let's recall some basic facts from measure theory. Probably many of you know these facts because I told something about them in the previous term. But anyway, let's recall some definitions. So suppose that X is a set. A is sorry. A is a sigma algebra of subsets of X. Sigma algebra. And mu is a sigma additive complex measure on A. I'd like to stress that mu is a complex measure, but it is finite by the very definition. So the value plus infinity is not allowed. By definition, the variation of mu is a function denoted in this way. It is non-negative, defined by the following rule. So if A is a set from our sigma algebra, then we consider all partitions of A, and for each partition we take the following sum. So the supremum is taken over all partitions of A into finitely many disjoint sets from our sigma algebra. So this is the variation of our measure. It's a standard fact that this function is actually finite. It's not immediate from the definition, by the way, but nevertheless, this is true. So this function is finite. And it's a positive sigma additive measure. It's a sigma additive measure. Okay, now let's suppose that X is not just a set, but is a compact Hausdorff topological space. We consider the Borel sigma algebra and denote it as follows. This is the Borel sigma algebra of X. This is the sigma algebra generated by all open sets. And suppose that mu is a sigma additive complex measure on the Borel sigma algebra. Then by definition, we say that mu is a Radon measure. Or a regular measure. If it is compatible with the topology in the following sense, for each Borel subset B of X, and for each positive epsilon, there exists a compact subset K of B, and there exists an open set U containing B, such that the variation of U minus K is less than epsilon. So roughly this condition means that each Borel set can be well approximated from the inside by a compact set and from the outside by an open set. Here is a simple but useful result which illustrates the importance of being regular. So suppose that mu is a positive radon measure on X. Positive radon measure. And suppose that P is a real number greater than or equal to 1. And let's consider the following map from the space of continuous functions on X to the LP space, LP of X mu, which takes each function f to its equivalent class with respect to mu. So roughly it takes f to itself, but strictly speaking not to itself, but to its mu equivalence class. So I claim that this map has dense image. So very roughly, this can be formulated as C of X is dense in LP of X. But it's important to remember that in general, this map is not necessarily injective. So if, for example, if the measure of each non-empty open set is strictly positive, then this map is injective. But in general, it can have a non-trivial kernel. The proof is a simple exercise for you. Actually, it easily follows from the definition of a radon measure and from Urson's lemma. Okay, let's now look at the space of all radon measures on X. So we introduce the following notation. We denote by M of X the set of all radon measures on X. This is easily seen to be a vector space, so the operations are pointwise. What is more important is that this is a Banach space. M of X is a Banach space. And the norm on the space, M of X, is given by the following formula. So the norm of mu is the variation of mu applied to X. So we have the following fundamental result, which will play an essential role in the spectral theorem. This result is usually attributed to Riss, Markov, and Kakutani. So the theorem states that if X is a compact Hausdorff topological space, then there exists an isometric isomorphism between M of X, the space of all radon measures on X, and the dual of C of X. And the isomorphism is given by the following formula. It takes each radon measure mu to the integral with respect to mu. So this is a standard result. It is not simple, but it's a standard result, and we will use it in our proof of the spectral theorem. Actually, it has rather interesting history. First, it was proved by Riess in the case where x is the closed interval on the real line. Later, it was extended by I forgot, probably Hunt to compact subsets of Rn. Then Banach and independently Sachs extended this result to metrizable compact topological spaces, and the general form is due to Markov and Kakutani. Okay, so this was a short digression into measure theory. Let's now turn to the spectral theorem. Actually, we are going to prove a more general result about representations of commutative C-star algebras, and to obtain the spectral theorem as a special case. So let's introduce some terminology related to star representations. Star representations. And the star modules. So suppose that A is a Banach star algebra. By definition, a star representation of A on a Hilbert space, H, is a star homomorphism pi from A to the algebra of bounded linear operators on H. For convenience, let's adopt the following convention. We will always assume that our algebra A is unital. And we also assume that pi is unital in the sense that it takes the identity of A to the identity operator on H. And let's also recall that such representation is automatically continuous, and that the norm of pi is less than or equal to 1. Actually, we proved some time ago that each star homomorphism from a Banach star algebra to a C-star algebra has this property. So now B of H is a C-star algebra, and this result applies. Let's now introduce a notion which is equivalent to the notion of a star representation, but which is sometimes more convenient for us. By definition, a star module over A is a Hilbert space H equipped with a left A module structure. So it is a left A module and a Hilbert space at the same time. And we require that these two structures are compatible in the following sense. First of all, the action of A on H should be continuous. And second, the involution on A should be compatible with the inner product on H in the following way. Over here, V and W are elements of H, and A is an element of our algebra. And also, since our algebra A is assumed to be unital, we also adopt the following convention. We assume that the identity of A acts as the identity operator on H. That is, the following formula holds. It's easy to observe that we have a one-to-one correspondence between between star representations of A and star modules over A. So there is a one-to-one correspondence between these two classes. Namely, if, for example, if we have a star module H, then we can define a representation pi of A on H by the following formula. And the other way around. So if we have a representation then we of A on H, then we can make H into a star module by using the same formula. So we let A dot V denote P of A applied to V. And let's also observe that if H is a star module over A, then the following inequality holds. Well, this follows from the fact that the norm of the respective representation is less than or equal to 1. Okay, so in summary, we see that we have two equivalent languages, so the language of representations and the language of modules. And sometimes it is convenient to switch between the two languages, depending on the situation. Okay, so these are our objects. Now let's introduce morphisms between them. Suppose that H1 and H2 are star modules over A. Then, by definition, a morphism from H1 to H2 is a bounded linear operator from H1 to H2, which is an A-module morphism in the usual sense of the word. So such that phi commutes with the action of the algebra. That is, the following identity holds. And by unitary isomorphism, we mean a unitary isomorphism of A modules. We mean that an A module isomorphism, which is a unitary operator at the same time. Unitary, so let's recall that unitary means that it preserves the inner product. Or equivalently, this means that this map is isometric. And we say that two star modules H1 and H2 are unitarily isomorphic. H1 and H2 are unitarily isomorphic. And we use the following notation in this case. If there exists a unitary isomorphism between H1 and H2. Okay. Let's now introduce a special class of star modules, which will play an essential role in our approach to the spectral theorem. So we have the following definition. Suppose that H is a star module over A, and let V be a vector in H. We denote by AV, with a line here, the following subset of H. So it consists of all elements AV, where A runs over our algebra. And we take the closure in H. So this subspace is called the cyclic submodule of H generated by V. So clearly this is the smallest closed submodule of H, which contains V. We say that H, the module H, is cyclic if there exists an element V in H such that the cyclic submodule generated by V is the whole of H. And each such element V is called a cyclic vector. A cyclic vector for H. Okay, let's now look at two typical examples of star modules. Example 1. Suppose that X is a compact Hausdorff topological space And suppose that mu is a positive radon measure on X. So I claim that L2, the L2 space, L2 of X mu, is a cyclic star module. A cyclic star module over C of X, over the algebra of continuous functions on X. With respect to the usual pointwise action, the action is pointwise. Here A is an element in our algebra C of X, and F is an element in our module L2 of X mu. Well, it's more or less immediate that it is a star module. Now, why is it cyclic? I claim that the function which is identically 1 is a cyclic vector. And this is essentially equivalent to the fact that C of X is dense in L2 of X. So the canonical map from C of X to L2 of X is, this map has dense image. So this means precisely that the function which is identically 1 is a cyclic vector for L2 of X mu. We'll see soon that this example is very typical, in the sense that actually each cyclic star module over C of X is of this form. Okay, now example 2. This example is more general and is not necessarily cyclic. First of all, suppose that we have a measure space, omega A mu, measure space. So the measure mu is not necessarily finite. Then it's easy to see that the L2 space, L2 of omega mu, is a star module over L infinity of omega mu. Again, the action is pointwise. Now suppose that, as an example 1, we have a compact Hausdorff topological space X. X is a compact Hausdorff topological space. And suppose that we have a measurable map phi from omega to X. Measurable map. So when I say measurable, I mean that it is measurable with respect to the Borel sigma algebra and with respect to A. That is, the preimage of each Borel subset of X sits in the sigma algebra A. So then such a map phi induces a star homomorphism, which will be denoted by phi dot. This is a homomorphism from C of X to L infinity of omega mu. And this homomorphism acts as a composition with phi. This is easily seen to be a unital star homomorphism. Okay, now L2 of omega is a star module over L infinity. And by using this homomorphism phi dot, we can make L2 into a star module over C of X. So L2 of omega mu becomes a star module over C of x. And the action of C of x on L2 is given by the following formula. So to act by A on F, we apply the homomorphism phi dot, and then take the pointwise product of phi dot of A and F. Here A is a continuous function on X, and F is an element of the L2 space. So L2 of omega mu becomes a star module over C of x. And let's introduce a special notation for this module. It will be denoted by L2 of omega mu phi. So the structure of the C of x module is determined by the map phi. And again, it's appropriate now to make an announcement. It will turn out, we will see this maybe at the end of today's lecture or at the beginning of the next lecture, that this example describes all star modules over C of x. And this is precisely our form of the spectral theorem. But let's first of all, let's look at the case of cyclic modules. So we have the following result, theorem 1. Suppose that X is a compact Hausdorff topological space. And suppose that H is a cyclic star module over C of x. I claim that H has the form described in example 1. That is, there exists a positive radon measure mu on X such that H is unitarily isomorphic to L2 of x mu over C of x. Okay, now to prove this result, first of all we choose a cyclic vector. So let V be a cyclic vector in H. Now, by using the Rees-Markov-Kakutani theorem, we obtain a positive radon measure. Well, first of all, we don't at this point we don't know that it is positive, so we obtain a radon measure mu on X such that the following formula holds. The inner product of Fv and V equals the integral of F with respect to mu for each continuous function F on X. Well, indeed, the left-hand side of this equality is clearly bounded linear functional on C of X. And the Rees-Markov-Kakutani theorem gives us the measure mu. So I claim that this measure is exactly the measure we are looking for. First of all, we have to show that this measure is positive. To show that mu is positive, we take any non-negative continuous function. And observe that there exists a non-negative, another non-negative continuous function g, such that g squared equals f. Well, this is clear. G is just the square root of f. Then the integral of f with respect to mu. So by our construction, this is the inner product of f, v, and v. Now we replace f by g squared. And we use the axiom that the involution on C of x is compatible with the inner product. So g is non-negative, in particular it is self-adjoint in C of x. And we can now write this in the following form by using the fact that g star equals g. And this is not obviously non-negative. So we conclude that the integral of each non-negative continuous function with respect to mu is non-negative. Now it's a simple exercise in measure theory to show that mu is non-negative. Okay, now let's begin to construct a unitary isomorphism between H and L2 of X mu. Let's denote by E the canonical image of C of X in L2 of X mu. So this is formally, this is the set of equivalence classes of F, where F is a continuous function of X. So this is subspace and in L2. And here, the square brackets denote the equivalence class. The mu equivalence class of F. And let's do the following simple calculation. So we take an arbitrary continuous function f on x, and we calculate the norm of f v squared. So what is this? This is the inner product of f v by itself. We can now write this in the following form. This is f star f v, the inner product with v. And by the definition of mu, this is the integral of f star f. And f star f is just the absolute value of f squared with respect to mu. In other words, this is just the L2 norm, the square of the L2 norm of the equivalence class of f. Why is this formula useful? This formula, first of all, it implies that we have a well-defined map. We have a well-defined map phi from E to H, which takes the equivalence class of each continuous function f to the vector fv. Well, why is it well defined? If f is almost everywhere 0, if f is 0 almost everywhere, then the above chain of equalities implies that fv is also 0. So this map is well defined. And moreover, phi is isometric. And this also follows from the above chain of qualities. Also, phi is a C of X module morphism. This is also clear from the formula, which determines our map phi. And the image of phi is dense in H. Because V is a cyclic vector. Also, we know that E is dense in L2 of X mu. So now, since E is dense in L2 of X mu, we see that phi uniquely extends to a unitary isomorphism from L2 of X mu to H. And this completes the proof. Okay, so this theorem describes the structure of an arbitrary cyclic star module over the algebra C of X, where X is a compact Hausdorff topological space. Before we extend this result to an arbitrary star modules, not necessarily cyclic, let's look at an operator theoretic corollary of this result. So suppose that H is a Hilbert space, and suppose that T is a normal bounded operator on H. And suppose that K is a compact subset of the complex plane, which contains the spectrum of T. Let's recall that in this case, we have a continuous functional calculus, gamma or gamma T, a continuous functional calculus for T. And as usual, when we work with a continuous functional calculus, we use the following notation. So if f is a continuous function on K, we denote by f of t the operator gamma T of f. So we know that the continuous functional calculus is a star homomorphism. So it is a star representation of C of K. And so our Hilbert space H becomes a star module over the algebra C of K. So we have the following picture. For each normal operator T on H, such that the spectrum of T is contained in K, we constructed a star representation of C of k on H. And it's very easy to see that this construction is actually one-to-one correspondence, because the inverse construction is trivial. If pi is a star representation of C of k, then we can just take the operator P of little t, where the little t is the coordinate, that is the inclusion map of k into the complex plane. So these two maps are inverse to each other, and so we get a one-to-one correspondence between normal operators on H, such that the spectrum of t is contained in our compact set K, and between the collection of all star representations of C of k on the same Hilbert space. So this representation theoretic point of view is very useful. Okay, we now have the following simple result in proposition. Suppose we have two Hilbert spaces, H1 and H2. Suppose that S is a normal operator on H1 and T is a normal operator on H2. And suppose that we have a bounded linear operator U from H1 to H2. So we take a compact subset K of the complex plane, and we suppose that K contains the spectrum of S and the spectrum of T, so that both H1 and H2 become star modules over C of k. I claim that this operator U is a C of k module morphism. If and only if it intertwines S and T, in the sense that this formula holds, and intertwines S star and T star. Well, the proof is very easy. To prove this result, we first of all recall the notation which was used at the previous lecture. Namely, for each polynomial p of two variables, x and y, we denote by p tilde the function of the complex plane given by the following formula. Then the Weierstrass theorem readily implies that if we restrict all such functions p tilde to our compact set K, so here P runs over the algebra of polynomials into variables, then this the resulting subalgebra will be dense in C of K, because it satisfies the conditions of the Weierstrass theorem. Okay, now let's now look at our condition. So US equals TU, and US star equals T star U. Well, by linearity, it's easy to see that this means precisely that that U intertwines P tilde of S and P tilde of T for each polynomial P in two variables. But now, since the polynomials are dense in C of K, and since the continuous functional calculus is continuous, we see that we can replace here P tilde by an arbitrary continuous function on K. So U f of S equals f of TU for each f in C of K. But this means precisely that U is a C of K module morphism. And this completes the proof. Okay, as a corollary, we get the following result. Our modules H1 and H2 are unitarily equivalent, unitarily isomorphic over, if they are unitarily isomorphic over C of K, then our operators S and T are unitarily equivalent. That is, there exists a unitary operator from H1 to H2 such that U intertwines S and T. That is, US equals TU. By the way, there is a stronger result. So I'll not prove it, but nevertheless, I'll give you a statement. This fact was proved by Fuglid and Putnam. Essentially, this result means that if S and T are normal operators, as in the previous proposition, and if U from H1 to H2 intertwines S and T, then the same operator intertwines S star and T star. So we see that, in particular, this result implies that the implication in the previous corollary is actually an equivalence. So if S and T are unitarily equivalent, then the same operator U gives us a unitary equivalence between S star and T star. And so U becomes a C of K module isomorphism, unitary isomorphism between H1 and H2. But anyway, we will not use this fact in our proof of the spectral theorem. Okay, let's now introduce star cyclic operators in Hilbert space. We have the following definition. We say that the bounded linear operator T on the Hilbert space H is star cyclic if there exists a vector V and H such that the following subspace of H, the linear span of all elements of the following form, where M and M are non-negative integers, is dense in H. So it's clear from the definition that the closure of this subspace is the smallest closed subspace of H, which is invariant with respect to T and T star. And each such vector V, if it exists, then we call such vector a cyclic vector, a star cyclic vector for T. Each such element V is a star cyclic vector. Okay. We now have the following simple result. Proposition. Suppose that T is a normal bounded operator on a Hilbert space H. I claim that T is star cyclic if and only if H is a cyclic star module over C of K. Whereas before, K is an arbitrary compact subset of the complex plane which contains the spectrum of T. Again, the proof is very easy. The argument is essentially the same as in the proof of the previous proposition. So let's look at the vector subspace, which appears in the definition of a star cyclic operator. And let's observe that this subspace can be written in the following form. So this is P tilde of T applied to V, where P runs over the polynomial algebra in two variables. Of course, we use here the assumption that T is normal. Well, now, if we now take the closures of these subspaces, and again apply the Weierstrass theorem, which implies that the restrictions of such polynomials P tilde to K are dense in C of K, then we get the following equality. But this is nothing but the cyclic submodule of H generated by V. And this completes the proof. So we see that T is a star cyclic vector for T, V is a star cyclic vector for T, if and only if V is a cyclic vector for H over C of K. By the way, there is a rather deep result due to Joseph Bram, which states that each star cyclic operator, each star cyclic normal operator on the Hilbert space is necessarily cyclic without star, in the sense that if we take all vectors of the form T to the power n of V, then the closure of the linear span is dense in H. So, but we will not use this result in our proof. But this is quite interesting and highly non-trivial, by the way. So it's clear that each cyclic operator is star cyclic, but the fact that the converse is also true is a rather hard result. Okay, now let's look at a typical example of a star cyclic operator. Suppose that X is a compact Hausdorff topological space. And mu is a positive Radon measure on X. Oh, sorry, not just compact Hausdorff, of course, not an arbitrary compact Hausdorff topological space, but rather a compact subset of the complex plane. So we are working with operators now, not with arbitrary modules, but with operators. Maybe let's better denote it by K. So suppose that K is a compact subset of the complex plane, and mu is a positive Radon measure on K. We denote by T the operator on L2 of K, which acts as the multiplication by the coordinate. That is, it acts by the following formula. When I claim that this operator MT is star cyclic, and if you take the function which is identically 1 on K, then this is a star cyclic vector. For the operator MT. Well, indeed, this can be immediately deduced from our previous example of a cyclic star module. In fact, this operator corresponds to the star module L2 of K over C of K, and we know that this module is cyclic. Otherwise, we can just look at the definition of a star cyclic operator and observe that the star cyclic subspace generated by the function which is identically 1 contains all polynomials in T and the complex conjugate function T bar. And by the Weierstrass theorem, this subspace is dense in C of K, and as a corollary, it is dense in L2 of K. So this operator is star cyclic. And we have the following result. This is theorem 2, which gives us a functional model for star cyclic normal operators. Functional model for star cyclic normal operators. So suppose that H is a Hilbert space and T is a star cyclic normal operator on H. Then there exists a positive Radon measure on the spectrum T such that T is unitarily equivalent to the operator MT acting on the respective L2 space. So in other words, the previous example describes all star cyclic normal operators up to unitary equivalence. To prove this result, we just look at theorem 1 and observe that together with our previous results, theorem 2 becomes just a special case of theorem 1. Well, indeed. So T is a star cyclic normal operator. So by the previous proposition, H becomes a cyclic star module over C of K, where K is the spectrum of T. So H, by theorem 1, H is unitarily isomorphic to L2 of K mu for a suitable positive Radon measure mu. And this implies that T is unitarily equivalent to the respective multiplication operator MT. And that's it. So our functional model theorem becomes a special case of the structure theorem for cyclic star modules over the algebra C of X. Okay, so and that's all for today. At the next lecture, our first goal will be to extend this functional model to an arbitrary normal operators, that is, operators which are not necessarily star